Hello everyone, welcome back to the channel. So today we are going to solve this question called Slavic G's favorite problem, and you are given a tree with n vertices. So this is the definition of tree they are given. So since trees bore you, you decided to challenge yourself and play a game on given tree. In one move you can travel from a node to one of its neighbors. Another node it has a direct edge with. So you start with a variable x which is initially equal to 0. When you pass through hi, x changes its value to x XOR wi. So if you don't know about XOR, it is better to check it out on this Wikipedia link. So where wi is the weight of the ith edge. So your task is to go from vertex A to vertex B, but you are allowed to enter node B if and only if after traveling to it the value of x will become 0. So if x is becoming 0 when we travel to B at that point, then only we are allowed to go to the B. So in other words, you can travel to node B only by using an edge I such that x XOR wi is equal to 0. So once you enter node B, the game ends and you win. Additionally, you can teleport at most once at any point in the time to any vertex except vertex B. So you can teleport from any vertex, even from A as well. So answer with yes if you can reach vertex B from A and no otherwise. So let us take a look at this sample test case. So here it is. Here n is equal to 5, a is equal to 1 and b is equal to 4. So our graph is like this is 1, this is 3, weight of the edge is 1, 2 and 3 are connected, weight of the edge is 2, 4 and 3 are connected, weight of the edge is 3, and 3 and 5 are connected, weight of the edge is 1. Okay, so you have to go from a is equal to 1 to b is equal to 4. So we have to go from here to here. So let's start traveling. So one thing to notice is that 0 XORed any value means 0 XOR with some value v always results in value v, and value v taken XOR with itself results in 0. So XOR is self-inverse operation. You are getting it right. So f of a is a. So it is self-inverse operation. So that is the thing. So you can conclude that you don't want to travel the same edge twice, right? Because it is self inverse operation. If you travel 1 to 3 and then you travel 3 to 1, then it doesn't make sense, right? You have the value at which you have the value which was already present with you when you were at 1. You travel to 3 and then back to 1. You didn't affect your value, so it doesn't make any sense. So crisscross operations like this, forward and backward, are of no use. This is the one key takeaway or observation you can say. So here I will start traveling here. 1 and 1, 0 and 1. The result will be 1 when I reach to the what you can say node 3. If I travel this edge, so 1 XOR 2, it will result in 3. Okay, it will result in 3. So I have value 3 here. Then I can notice that to go to 4, I have to travel this edge at least once, and when I travel this edge, my value of x before traveling to the edge must be 3, because 3 XOR 3 is only 0. Okay, so that's why I can teleport from 2 to 3 now and then travel to 4 from 3. So that way I can reach B with my value x XOR weight of that edge as 0. So that's why in this case answer should be yes. So it is indeed, it is a yes. You can check it for all other test cases also, sample input test cases. So I will tell you general logic behind these. So what is happening is that, suppose this is the node A and you want to reach some B. These are some edges connected to B having weight W1, W2, W3 and so on up to Wi, you can say Wi, and these are some edges going out of A to any of the vertices. Those weights doesn't really matter. So what I can infer is that I will perform a DFS on A, means I'll start traveling the graph from the vertex A, and whenever I get my x to the any of the value w1, w2, w3 or so on up to wi, if my x is equal to wi for any x, means at any point, suppose here, suppose vertex is there, suppose here one vertex is there, and path from A to this vertex, after completing that path my value of x will become, suppose if it becomes wi, then I'll directly teleport to the vertex, to the vertex of, means to the vertex which will have wi weight connected, wi weight of the edge connected to the B. So I will directly jump to that vertex and my task will be accomplished. Okay, so that is the thing. And notice that while performing DFS, suppose node was there, this node was there, this node was there, when I will go to here, I cannot go further B. You get my point, right? You cannot go further B, because if you enter B, your value of x must be 0. So DFS won't work for the nodes which are not connected directly to the A. Not connected directly to the A means the path between A and those nodes must not contain B in it. Okay, and if it contains, the value of x should be 0. So that is the thing. uh, Basically this is the solution. We can head towards the code. See this. So this is visited array to maintain for DFS function. This is the graph, and set will keep inserting value in set. Whenever we go to the vertex, we will insert that value of x to the set, and if the value in set, if any of these values match any one of the value in the set, then we are done, right? So another thing is that it can happen that you can say that, so another thing which can happen is that, suppose A doesn't, the paths coming from the A doesn't have access to these nodes we talked about, right? These nodes which DFS from A will not reach. So it can happen that, suppose this is the nodes. So so suppose from this node I jump from here, and from here I keep on doing XOR, and then here I will reach the WI. It also can happen, right? So for that we have to perform DFS on B as well. So we will perform on DFS on B and check if the resulting value at the every vertex is present in set or not. If it is, then answer is yes, or if it is not, then answer is no. So that is basically the solution. So code is pretty simple. Every aspect of this solution is implemented in the code. So finally you don't have to miss this part. Okay, miss this part, this thing, resetting all the values. Okay, you don't forget that for every test case. So uh, check for the code. If you have any doubts, let me know in the comments. I'll try to clarify them by giving examples, sample test cases. So yes, this is it. So universal bool is doing so nice work. You can go through code. I'll leave the link to the code in the description. Make sure to check it out. And thank you for watching the video. Stay tuned with the channel and see you again. Goodbye. Take care.